All right, let's continue our energy accounting. Energy accounting, basic, again, trust me on this. If you're doing energy accounting, I think the clearest structure to think within is energy changes from any interactions outside of our system between the earlier and later states cause the change in energy of our system or objects. And the way we look at it is the energy earlier, mechanical, kinetic and potential, anytime that's there. And then you go back and you take the energy later, kinetic and potential, and then you look between the states. Okay, so let's try to do that. If this is 0, then that's conservation of mechanical energy. Here's another couple of problems. Let's throw in some springs. We know what that is. So here's a spring, and it's compressed. I'm trying to shoot a rocket up into space. Okay, so there's my little situation here. And so I like to label my states 1, state 2, and state 3. And I can look at any of those two. I can go from 1 to 3 straight away with energy analysis. That's fine too, right? I can do from 1 to 2. Let's take a look at these. At this moment, I have to tell you a little bit about this problem. So it's at rest. So I'm going to give you that there's no speed happening here. Also, there's some spring constant, lowercase k, right? So draw it however you want. Let's not confuse it with kinetic energy. So that spring has a certain strength per centimeter compressed or stretched, meter compressed or stretched, right? It has a certain strength. All right, and so there it is, loaded up, we've compressed it. Now, in fact, at this point here, we're going to say that the stretch, some people use x, I'll use s, the stretch is 0, that is, it's equal to s equilibrium. Okay, so we're going to release the spring, it's going to go. Now, the moment that the spring gets to that point, it starts pulling itself back because as it passes equilibrium, it starts pulling itself back. The rocket, however, will take off with a certain speed of v2. Okay? And then it's going to go up here, and we'll say this is the top. Of course, we can look at any time, and it's really not that big a deal, just as long as we've got enough information. And we know then at the top, v3 is 0. And of course, we know what that means about the kinetic energy. Fine, so let's look at it, what we can say. Let's try from 1 to 2. Let's do this quickly. All right, so the first thing to do, if you get in the habit, you're good. Change in energy from 1 to 2 is energy what? 2 minus energy 1. Cool. All right, now let's work backwards. So this is, how much energy do I have at 1? Well, I've got no kinetic energy. Have I got potential energy of gravity? It's up to you. Isn't that weird? I mean, I could say it's 0, or I could say it's negative, or I could say it's positive. Remember our good old friend? You get to choose where 0 is, but above it's positive, below it's negative. Strange, right? It's really only the changes that we're keeping track of, because our equation inherently has changes. I am going to choose, so this is kind of nice, I'm going to choose H2 equal to 0. Okay? So that means here. Now, we're not worrying about the size and shape until the next topic of rotations, but so we'll just put it right there. And so it's at a certain, or maybe to the center, whatever it is. But it's going to compress down from here down to there is going to be my H1. And H1 is the same as my S1. So that's the interesting, you've got to think physically. The algebra is later. The height is the same as the amount compressed. But depending on how we do this, we might want that to be a negative number. So if S1 is negative, fine, but whatever we know that H1 is less than 0 because 0 is here. Okay, so there's 0. All right, so I've got that. So that means that at that moment, I've got kinetic energy 1 plus potential energy of gravity 1 plus potential energy of spring 1. All right, let's get specific over here then. That's 1, oh, wait a minute, that's 0. I don't need to write that, right? And then I've got mgh1, which is S1. And then I've got 1/2 k S1 squared, so it doesn't really care whether it's plus or minus, right? So remember, H1 is equal to at least the absolute value of S1. So you have 2 there. And what do I have at E2? Just look. Again, not from memory, it'll just short circuit your brain. At state 2, I have kinetic energy, 1/2 mv2 squared. I've got potential energy, it's equal to 0, which doesn't mean none, it's just a reference, but I did set that 0, so I don't have to put that in. And then I've got the spring, wait a minute, the spring's unstretched, so 0 and 0, you don't need to write that in there. And I'm good. Really? That's all you have to do? It seems so complicated. The tricky one was realizing this. Huh, interesting. And then from here to here, are there any changes in energy? Energy added or taken away by interactions? And the answer is yes. The interaction with gravity, which is the interaction with Earth, and the interaction with the spring. But again, those were accounted for already here. You'll see it later. So, short of the interactions from potential energy, from the non-conservative forces, we got nothing. And now, solve away. Whatever you got, whatever you don't. Is M a common factor? No, you can't cancel M. You can't do that, right? You got to be given or find or whatever. What about 2 to 3? Fine. Watch how fast. You know, you're going to start writing this like 2 to 3 equals energy 3 minus energy 2 equals, and then I just work my way back here. At 2, what do I got? It's that, right? 1/2 mv2 squared. That's all I got at 2. And state 3 is here. What do I have here? I got mgh3, so I might want to know how high it went. Oh, sure, you could use kinematics, but why? Energy is such a beautiful technique. It is kinematics. It's just in disguise. You'll see that later. No kinetic energy. What about a spring? Yeah, there's a spring. It's not in the game. It's not in the game, so that's it. Right? It's done. It's not there anymore. And from there to there, if we have no air resistance, that's it, right? Don't memorize that equation. Kill the equation, right? Right? Pause it. Now do 1 to 3. Pause it into, okay, you're done. Cool. 1 to 3, delta E, 1 to 3 is E3 minus E1. All right, working my way backwards. E1, I got this whole thing, right? So that's my E1. E3, I just had the mgh3, right? Cool. And then from here, hey, wait a minute. Did that work? Can I do it? Are there any energy interactions other than the conservative ones of gravity and the spring? No, unless there's friction in there. Sure, then you're going to end up losing, not ending up as much. So you still get to have that. It's still conservation of mechanical energy. You don't necessarily have to go 1 to 2, 2 to 3. You can go 1 to 3 straight away if you want. If you're throwing, remember 1 to 2, I am adding energy. 2 to 3, it's conservation of mechanical energy. So now check this one out. Now we're going to get a little geometry in here. All right. So start here, look at it, fill it in, work on your speed, because speed does matter, especially when you get to upper division. Hand's going to cramp. Suppose I have a ramp that's for now frictionless. We'll get friction in there. We'll add that. It'll go right into this format beautifully. All right, so let's throw a ramp in here. And notice how I draw this as a process, right? So I really encourage you to not have a cluttered picture. I'm going to have a spring catcher here. Put it right there, okay? Here's my angle. Let's call it theta, right? 30 degrees, whatever that angle is for my incline. And then I've got my object of interest that I want to look at. I'm going to have a block. And I'm going to release from rest. Okay. Now you can do this side by side. You can also do it down below. I think I'll do this side by side actually. This will be a little bit. So let's go over here. and I'm going to release it, and I'm going to break it up into 3 states. A problem might ask these sorts of things. So draw your angles not 45 unless it is 45, smaller or larger than 45 so you can clearly see them. And I'm going to look at the state, just a little bit of care here. It's a little bit too steep. I like that better. What did I say? That thing is still there, but I don't know what's attached to. It better be attached to a wall or something, right? And there it is. There's my spring catcher. It's got a spring constant. I don't know. Okay, maybe I'll be given it. Maybe I'll look for it. Who knows? And I'm going to look at the moment just before it hits. Okay? And then I'm going to look at the moment where it stops. And you know what's going to happen. That spring is going to compress. And so it's going to stop. Okay? All right, great. Now, how do I do this? Oh my gosh, it looks so difficult. There is a little bit to work on here. So here's state. Clearly 1, 2, 3. And then let's see, I was given V1 is 0, so I know that means kinetic energy. 1 equals 0. What do I have to do again here? I got a spring, so there's no energy when it's in equilibrium, but I also have gravity, right? So clearly, if I'm not moving vertically, and there's no change vertically, then you don't need MGH, right? Because again, the only thing that matters is change. So if you stay like this, and the H is always the same, call H0. You don't even have to think about it. Okay, but here the H is changing on purpose. So let's take a look at this. I need to find a place where H is equal to 0. Okay, I'm going to choose it. It doesn't matter. You could choose down here, you could choose it here, or you could choose it there. I'm going to choose it here. It really doesn't matter, and you should get over any worries that it does. So I'm going to set H equal to 0 there. Now that's going to be up there. Now notice the picture's kind of nice, right? I can see that. Now you're going to have to really draw a nice picture here. So let's go 1 to 2. Fine, 1 to 2. All right, I know the game. I'll think about it in terms of the changes from 1 to 2 equals the energy at 2 minus the energy at 1. Fine, da, da, da. And let me give myself some room here. Energy at 1, what have I got? I got nothing. Oh, I got no kinetic, right? So that's whatever. That's kinetic 1 plus potential energy gravity, spring at 1. Fine, you know that. So this is from this level, wherever that level is, where my block ends up there. That's my H1. Now this is H equal to 0, so this is going to be a positive number. Again, you can call coordinate system positive or positive. That's still more. So that's MGH1. Fine. You could use trigonometry if you're given this height, fine, or this. Just draw your triangles. All right, that's all I got. And energy at 2, what do I got? Well, I got 1/2 mv2 squared. Why don't I have mgh2? Because h2 is set to be 0. That could be 0. Fine, that's 0 and whatever. It's going to give you the same answer because changes are the only physical thing. I said there's no friction, so good. There's that, and voila, you can do it. M's go away, and what do you find? You could do this. Be careful doing this stuff in your head, but V2 is equal to 2gh1 square root. Okay, so that's exactly what you could get with kinematics and using force analysis, kinematics, the same thing. Why did you do it this way? It's faster, it's easier, right? Okay, good. Now there's that. Now what about from 1 to 3? Can I do that? Sure, I can do that from 1 to 3. From 1 I've got still the same energy, and 3 I've got this here. Or 2 to 3, I've got that energy, and 3 here. So you can do that too. Now here's where it might get a little tricky. Now I'll let you set that up. But suppose I knew something about this spring. Suppose that I knew that the spring had a length of L. And then it goes down here and it compresses some amount, S3. And then, of course, it stops, so there's no kinetic energy, but there is potential. So what's H3? This is not energy. I mean, it's part of energy analysis, but it's trigonometry, it's triangles. Let's see this. This is hard to see. So what do? I get out some paper, and I really draw this guy. As big as I can. I'm going to start this guy up here. Length L. And then it's going to go down. S3, and it's all compressed here, right? I call this height, or wherever it started, right? I'll just measure from there. H2 equal to 0. And here's my H3, which is less than 0. All right, what else can I say? I don't know, just say when you're problem solving, you're stuck, just write something you know is true. I've got a theta. Fine, I know that this height here, above theta, that blue one, let me see, I don't know, I'm going to call it H. Sine of theta is H over L. Fine. Okay, well, that's something I could write. But wait, that theta is the same as this theta, isn't it? So this is H3. Oh, hey, what about this? What if I say, if I just look at that triangle, the sine of theta is H3 over S3. So they're related. I don't know, and H3 is equal to S3 sine theta. But remember, it's negative, so if you're taking those as positive, make sure you throw a negative in there because of that, right? And then where's it go? MgH3, you throw it in there. So this is perhaps, the more difficult thing is actually just seeing where your H is. So choose an H equals 0, that's fine, up there is fine, anything is fine. It'll all work out. Occasionally you're going to have to draw some angles, right? And figure that out. Let's do one more. How are we doing?
About 7 minutes.
One more little bit. A pendulum, right? Now, I shouldn't do all these for you, but I do want to show you some tricks of the trade. Really, the tricks then you see are not in going, earlier energy, later energy, the change between those earlier and later states. The trick now is sometimes just setting H equals 0 and seeing some triangles. For example, a pendulum. I'm not going to do it all for you. You can choose any two states. Remember, the change in energy between those two states might not be 0. So, we'll get there. But this is getting really quite good. You can just knock this stuff out, the basics. This is the basics. So I've got a pendulum. I'm going to swing that guy back and forth. Notice it moves along an arc, circular arc, length L. All right, so I'm going to draw this, and who knows, here's hanging from here, pull it back. Here's my vertical line. Okay, and let's draw this, and let's pull it back, here. Right. And then it's going to swing along a circular arc. If I push it, it'll go up higher. If I don't, it'll just go to the same height by conservation of mechanical energy, right? So I got energy potential going into energy here, kinetic plus, and then I got energy here, potential. But potential is relative to H equals 0, so I need to choose an H equals 0 place. So why don't I choose this lower? Anything is fine. Anything is fine. Energy doesn't matter. It's the changes in energy is relative. The change in energy is physical. Okay, cool. So I'm going to choose this 0, 3, 3 lines defined as or set to be 0, chosen as 0, fine. And I know that I've got my picture here, and so at that instant I've got this ball going here. I'll call that V2. Let's call this 1, and I'll say I release it from rest. You could push it, whatever the case. And then I've got this, and I've got H1. Let's say I've got a length of this string is equal to L, and let's say I've got an angle here, theta 1. Good to subscript your angles if they're changing. All right, so what have I got? Well, let's see, I'm going to go 1 to 2, change in energy, 1 to 2 equals energy, mechanical energy at 2 minus mechanical energy at 1. Fine, at 1, what have I got? I got mg, h1, that's all I got, right? It's not moving. And at 2, I've just got 1 half mv2 squared. No mgh because I've set that equal to 0. Between the two, hey, wait a minute. Any interactions other than gravity? Yes, tension. But tension in this case is just turning it. The tension is neither speeding it up nor slowing it down. We're going to get to this when we talk about the concept of mechanical work. But the tension is not speeding it up or slowing down, it's just redirecting it. It's just changing direction. And energy is not a vector. Direction doesn't matter. So that tension is doing no, we'll say later, work. And that it's making no difference other than changing the direction, which doesn't change energy. Important point here. So that's a beautiful thing. What's the problem here? The problem is H1. What's H1? Well, let me show this to you. How far is that? Oh, that's the length of the string, isn't it? That's okay. Huh. I want to know, I called that, so I want to know how much that is, right? Huh. Well, I know that. Oh, what's this? What's that? Let's see. That right there. Hey, that's this. It's adjacent to the angle, so that's L cos theta, isn't it? From there to there. Hey, this plus that, L cos theta plus H3 is equal to L. Or you can look at it another way. H3 is equal to L minus L cos theta, theta 1, right? And there you got it. I mean, don't memorize, but you can, if you want, you'll see people often write this. You go, oh my gosh, how'd you get that? Just look and see that. So H's can be a little tricky here. You got to set your 0 point and then measure. Well, that could have been H equals 0. Fine. That could have been H equals 0. You still have to deal with this. Okay, I think we're good. I think we're gonna talk about potential energy and energy versus position graphs next, then collisions, and then we will do the advertised derivation, full derivation of the work energy theorem.